Okay, so just like when we talked about limits of functions, if we were to apply the definition of the derivative in order to compute the derivative of every function, it would be very difficult in general because some manipulations would be really hard, and that's why we have this some algebraic properties that allow us to um, manipulate derivatives and use um, some techniques to compute the derivative to more easily compute the derivatives of some functions. Okay, and these are these five. Okay, so the derivative of the combination of a function of linear combinations of functions is the linear combination of the derivatives, and this goes from the linearity of the limits. The product rule, so the derivative of the product is the derivative of the first function times the second function plus the derivative of the second function times the first function. Now the chain rule, which is the derivative of the composition of two functions, is the derivative of the first function composed with the second times the derivative of the second function. The derivative of the quotient is this rule, f prime g prime minus f g prime divided by g squared, and then the derivative of the inverse function is 1 over the derivative of f but evaluated at the inverse of the point. Okay, and then we're going to go over the proof for the five properties so that you get a sense of them, right? So the first one is it goes straight from the linearity of the limits. Okay, so we want to evaluate the derivative of this function lambda f plus mu g, where lambda and mu are real numbers at a point A. Okay, and then this, applying the definition, this is the limit when x goes to a of lambda fx plus mu gx minus, and then lambda f a minus mu g a, right? All of this divided by x minus a. But then you can see, it's easy to see that you can separate the parts related to f and the parts related to g, right? So then we have the limit when x goes to a of fx minus fa, and then we have a common factor lambda, we can take it out, divided by x minus a, and then the same thing, minus mu limit when x goes to a of gx minus ga divided by x minus a, right? Now this thing here is the derivative of f at a, and the second fraction, this limit here, is the derivative of g at a, right? So we can say that this is, well, we can write it like this. Minus mu, sorry, this is minus, so it's plus mu g prime at a, okay? So the same thing. Okay? Now the others are right like this, okay? This demonstration, these proofs are all very similar, right? It's just applying the definition of the derivative and then do some algebraic manipulations, okay? The derivative of this function f times g at a is just the limit when x goes to a of fx times gx minus fa ga, right? Divided by x minus a. Now I want to get a factor f prime here. So what I want is to introduce this this new term minus fagx, right? Because if we have that, now we can take a common factor gx, and then this is fx minus fa divided by x minus a, this is f prime, right? And then we can say, well, but if I've summed this, so I subtracted this, so I have to sum it again, so then I have f of a gx minus f of a ga, right? divided by x minus a. Okay, this is plus. Okay, we're just adding and subtracting the same term, and this is the same thing, separating the fraction in two, right? Now, the first limit, we take a common factor gx, but the limit, so we can write it like this, right? The limit when x goes to a of gx times the limit when x goes to a of fx minus fa divided by x minus a, and then we have plus, and we have fa out, and then the limit when x goes to a of gx minus ga divided by x minus a. So this is g at a, f prime at a, right, plus f at a, g prime at a, okay, which is what we wanted to prove, right? So let's go for the chain rule, which is a very interesting one. The chain rule. We have the derivative of f composed with g at a, which is actually this is the limit when x goes to a of f of gx, right, minus f of ga, that's what the composition means, divided by x minus a, right? But then you see that there's a gx, ga. If we had a gx and ga in the denominator, we could write this as the derivative of f at g, right? So let me multiply and divide by gx minus ga, right? So this is f at gx minus f at ga divided by g at x minus g at a times, and then we have g at x minus g at a divided by x minus a, right? Now this thing, the limit of this thing is going to be, let me write it like this, x minus a, g at x minus g at a divided by x minus a. Okay, this is going to be g prime. Okay, and then we have the limit, and let me rewrite this. Okay, when x goes to a, then we can have that y goes to, we can call it g of x, let's call it y, right? Let's call this y is equal to g of x, right? When x goes to a, y goes to g of a, right? So then we have f at y minus f at g of a divided by y minus g of a, right? So now this thing, as I said, is the derivative of g at a. And now this is the derivative of f, but at g of a, right? So in other words, this is f composed with g, right, times g prime, all of this at a, okay, which is what we wanted to prove here. Okay, let's go for the fourth quotient rule. The quotient rule says, so we have f divided by g prime, right? So we can think of this as f times 1 over g prime, right? And then apply the product rule, right? This is f prime divided by g plus f times 1 over g prime, okay? But the question now is, what is 1 over g prime, right? What is this? Now 1 over g is, if we write this function f of, phi of x is 1 over x, right? Then 1 over g is phi at g, right? So the derivative of 1 over g is going to be, sorry, this is not this is phi composed with g. So the derivative of this is going to be, applying the chain rule, is going to be phi prime evaluated at g times g prime. Okay, so what's this, the derivative of this? Okay, let's see, what's the derivative of 1 over x prime? So this is the limit when x goes to a, or let me in this case, let me write it like this. When h goes to 0 of 1 over x plus h minus 1 over x divided by h, then we take everything in the same fraction, so we have x times x plus h, right? And then we have x minus h, all of this divided by h, right? X and x cancel out, so then we have the limit when h goes to 0 of minus h divided by x times x plus h, right? H and h cancel out, the limit when h goes to 0 of this is 0, so then we have x times x squared minus 1 over x squared, which some of you already know, right? So then we can write this like this. This is f prime divided by g plus f, and then the derivative of 1 over g prime is phi, which is the derivative of 1 over x, which is minus 1 over x squared, composed with g, so this is 1 minus 1 over g squared times g prime. Okay, and so this is f prime over g minus f times g prime over g squared. If we want to take everything in the same denominator, we have g squared, and then we have f prime g minus f g prime, which is what we wanted to prove. Okay, obviously provided the g is different from 0. Okay, and then the final property is that the derivative of the inverse is 1 over the derivative of f at f minus 1. Okay, well, in order to prove this, well, we're going to use this property of this of the inverse, right, which is that f composed with f minus 1 at x is going to be x, right? Now we differentiate both sides. The derivative of x is 1, as we know, so this is going to be this, and but in order to compute this, we need to apply the chain rule, right? So this is f prime composed with f minus 1, right, times f minus 1 prime at x equal to 1. Now if we solve for this, this is f minus 1 prime is going to be 1 divided at x, okay, is going to be 1 divided by f prime composed with f minus 1, okay, so it's like f prime evaluated at the inverse of that point, okay. So using this in particular, this last rule, we can prove that we have that the derivative of f ex is the same, right? Ex. Now if we have f minus 1 of x is the logarithm, right? What's the derivative of the logarithm? Okay, the derivative of the logarithm is 1 over f prime, which is ex, right? So it's the derivative of ex, evaluated at f minus 1, okay? So e to the logarithm of x. E to the logarithm of x is 1 over x. So this is the derivative of the logarithm. Okay? Could also be the case that we, instead of thinking about the logarithm, the natural logarithm, we have our, let's say, the logarithm in base a, right? Which is let's call it the inverse of our function f a to the x, okay? So now what's the derivative of this function? Well, as usual, we can write this like this: e to the x logarithm of a, and now the derivative, okay? And then this is using the chain rule, right? This is e to the x composed with, this is e to the x composed with x logarithm of a, right? This is what it is. And so the derivative of this is going to be e to the x, the derivative of this, but evaluated at this function, so e to the x logarithm of a, or in other words, a to the x, times the derivative of this, but the derivative of this is going to be the logarithm of a. Okay, so in other words, the logarithm of a times a to the x. Okay, so now we have the derivative of the logarithm of x in base a, okay, is 1 over this derivative, but evaluated at the inverse. Okay, so this is a to the log a of x times the logarithm of a, right? Now this thing is x because it's the same function, so this is 1 over x logarithm of a. Okay. Now let's see a couple more. Using the same thing, we have function f is x to the alpha, where alpha is any real number. Okay, we have seen that x to the n, when n is natural, the derivative of f, if alpha is natural here, would be alpha x to the alpha minus 1. Okay, now we're going to see that this is also true if alpha is a real number. Okay, again, we can write f as e to the alpha logarithm of x. Now f prime, applying the chain rule, this is going to be, this is ex, right, composed with alpha logarithm of x. So the derivative of this is going to be the derivative of the exponential composed with this to the times the derivative of this, which is alpha divided by x, right? Now again, this is equal to x to the alpha times alpha divided by x, or in other words, alpha times x to the alpha minus 1, okay, which is the derivative that we were searching for. Okay, and finally, let's do one of those trigonometric ones. Okay, so we know that the inverse of the sine, right, is the arc sine. We call it like that. What is the derivative of the arc sine? Well, the derivative is 1 over f prime, which is the cosine of x, right? The cosine, but evaluated at the inverse, okay? Instead of the cosine of x, the cosine of the arc sine of x, right? Now, how do we express this in an easier way? Well, we know that the cosine of x is the square root of 1 minus the sine squared. Okay, so then this is equal to 1 over the square root of 1 minus, and then the sine squared of the arc sine of x. But this is the same as x squared. So the derivative of the arc sine is 1 over the square root of 1 minus x squared. Okay. Now, using the same technique that we have been using, you can compute the derivative of the tangent and the arctangent. Okay, for the tangent, you need the derivative of the quotient, and the arctangent once you have the derivative of the tangent, right? And finally, this is a table of the derivatives that you need to know. Okay, some of them we have proved already: the derivative of the constant, x to the alpha, e to the x, a to the x, the logarithms, the trigonometric functions, the tangent and the cotangent, you can prove on your own. The arcsine, we have seen the arccosine, you can prove as well. The arctangent, arccotangent, you can prove. The derivative of the hyperbolic sine and cosine are just derivative of exponentials, right? So it's easy to see them. And the same with the hyperbolic tangent and cotangent using the quotient rule. Okay, So these are the derivatives that you need to remember.